Okay, so we saw this thing. Let's see if I can zoom in here. So we saw this thing yesterday. We have our, say, naive database. We have some kind of system for keeping track of customers and orders. So this does work, right? So if we had a system, we just started a business or whatever, we were implementing something to keep track of customers and orders, this is fine. And as long as our business stays relatively small, maybe this isn't such a problem. But as the business scales up and you get more and more orders, you start encountering all kinds of edge cases. So could we maybe just talk about some of the drawbacks of the current database design here?
You have to repeat the address, like for every time that Sally Smith or Bob Jones orders something, you have to repeat the address.
Okay. So Sally Smith orders another lamp. So she orders another lamp. So what's different is right here basically, but we still have to include all of this other information. So if we have, again, millions of orders, then we're potentially repeating the same data millions of times. Okay, so that's one issue, is that there's some repetition. So even though we have a new order, her address is still the same, but we have to include it again.
You can't sort by last name, and then you can't sort by individual address pieces.
Okay, yeah, so this is just kind of one chunk. So this is maybe not really atomic. This is not an atomic value. So we have two pieces of information in one column, and in the address we have more, maybe three or more. So obviously address could be a lot more complicated, but yeah, so our columns do not contain atomic values. So that's another problem.
For each order, do you have to repeat the age?
Yes. Yep. So that's another case of repetition. We have all of this customer information that we end up having to repeat.
And we're also persisting calculated data unnecessarily.
Right. So if we have their birthday, we should be able to derive their age, right? We shouldn't need to specifically include that. So there's, we're in some ways we're storing the same piece of data twice, even though it's not, it's not literally the same, or I guess numerically the same, but it's easy to get this. So this is a case of normalization. So you'd want to normalize the data so you don't have redundant information. Anything else?
Order total is also a calculated field.
Right. Yep. So we have the same issue over here, where we can, so if we assume that this is kind of a simple calculation, then order total is just repeating data that we could derive from elsewhere. Now there are cases, so we talk about, so initially when we do this, we want everything kind of to be as normalized as possible, but there are reasons, real world applications, there are reasons to denormalize data sometimes. If you're making lots and lots of queries, and let's say, we make lots and lots of queries and we only really care about the order total, then you might want to trade. And let's say maybe this is an expensive calculation or something. You might want to trade increased memory usage for decreased, basically for increased efficiency on a query. So you can do that. So even though, there are situations where you might want to have redundant information to speed up queries. Any other issues?
And also you're repeating lamp and order cost, like order item and order cost every single time as well.
Okay, right. So the lamp, we're saying how much the lamp costs every time, even though the cost of the lamp hasn't changed. Okay, so that's another repetition. What if Sally Smith gets married to Bob Jones? Maybe her dress, they move in together.
There's nothing that's identifying that that's the same person.
Yeah, so now we have a situation where if we want to look up Sally's order history, we have to, outside of our system, we'd have to know, maybe we'd have a post-it note on our monitor or something. Sally got married, and so anytime we run a query, we have to account for that. Now she's in the system, but she has 2 different addresses and 2 different names. So we're putting ourselves in a position where our data integrity is an issue. So we could, of course, once Sally changes her name, we could run some kind of update on our system and just change Sally Smith to Sally Jones and change all the addresses. But we'd have to remember to do that, and that might be prone to error. And also we're having to change all of this data that's just repeated. So I think, yeah, so I think those are the basic problems. Cindy, do you have something else?
Yeah, I was just going to say there's no unique key to identify, like 2 people could be named Sally Smith.
Right, yeah.
And yeah, there's nothing unique to identify them.
So if we have someone else sign up who just happens to be named Sally Smith, because people are, allowed to have the same name, and she lives she lives down the street. So if we want to look for Sally Smith's orders, now how do we know which Sally Smith? So having some kind of key or column that uniquely identifies any instance or entity is a good idea. So there are 2 ways to get keys. One is something called a natural key, which in this case, name is probably not a very good natural key, but there are instances or examples where some piece of data might be unique. So for example, a username or an email address. So you could require in your application, you could require a unique username, and you could potentially use that as a key. Although that's not necessarily the best way to go. So one is a natural key, which is kind of simple, just one piece of data. You can also use combinations of fields or combinations of columns. So you could do a combination of name and address. And if we assume that that's going to be, globally unique in our database, we can use that as a key. But the kind of simplest thing, and what we'll end up doing, is to use a synthetic key. So we'll let the database take care of it, and it'll just basically assign a number that will be unique. So we'll create a specific field that will just be called ID or something like that. And anytime we create a new user, that user will get a unique ID. So it won't matter if there are 2 Sally Smiths, and it won't matter if the 2 Sally Smiths happen to be roommates and have the same name and live at the same place. That won't affect our application. Okay, are there any questions about that? So let's start pulling this out. So we have this huge table. We have one huge table that's supposed to represent this application. So let's start pulling out this information, and let's create multiple tables. So if we think about, we could think about the entities that we have. We can sketch this out. So one common tool, or tool or approach that people use when they're designing databases is something called an entity relation diagram, or an ER diagram. So an entity relation diagram is basically, you have your application, right? In this case, we're starting from something, but maybe you're starting from scratch, and you want to think about you can think about designing an application with classes, right? So if I want to design an application to, I don't know, represent users renting movies, for example, you have to think about what are the classes. So I need a user class, and maybe I need a inventory class, and whatever other classes you need. So you kind of pull out all the basic entities, and then you figure out what those entities need to have and be able to do, and how they're connected to each other. So you'll do something similar with databases. So we have the first step you want to do when kind of designing a database is figure out all of the entities that you have. So you don't need to get into all of the details about maybe how everything is connected and all the nitty-gritty attributes, but just at a high level, what entities do we need? So let's focus initially on, well, so let's start breaking this down into entities. So what's a good first entity to have?
ID.
Okay, so an ID would be a field or an attribute. So if we wanted to keep this as one giant table in our database, then yeah, we could definitely improve this by adding an ID. An ID would represent, maybe not, in this case, maybe not a user exactly, but probably like an order. So this would be ID1, ID2, ID3. You could do that, but that's not really an entity. That's more of a field or an attribute.
We could pull out the name if it was separated into first and last.
Okay, so we could do name.
So would it be a customer class or?
Yeah, so I think that's probably so we could break it down into very, we could break it down very fine grained and have something like name and have like a name table with first, last, middle, maiden name, whatever, aliases, suffixes. So you could certainly break that down in the table depending on application. But if we're keeping this, but right, I think probably customer is a good entity to start with. We can take customer, and then if we need to, we can break down name further. So so if you think about an analogy to creating classes. So if this were an application and we wanted to create a bunch of classes, you'd probably want to have a customer class. So there's some, I guess, controversy. Should this be singular or plural? I'll leave that up to you. It's be customer or customers, depending on whether you think of it as like a set of possible customers, maybe plural, or it's just like an instance. So we have customers. So any other, what should a customer have? What are the attributes that a customer should have probably?
The primary key.
Okay, so yeah, so let's say everything should probably have some kind of primary key. We can call that ID. That's what it's usually called. What other information should a customer have?
Now they can have a name, a first and a last name.
Okay, so we could split that up. And so again, we could keep this the same and do name and then have both first, last, but let's make first, last. So what other information is kind of belongs to a customer?
Their address.
Okay, you can do address. Now we have this, so we'll keep it like this, but again, we have a similar issue with name where address maybe isn't really a simple, it's not really a simple field, but let's leave it like this for now.
And their birth date.
Yeah, so let's go ahead and include birthday. So we have customer, and based on what we have here, we have an ID, which will be, let's say we'll let Postgres, in our case, we'll let Postgres take care of handling this, but we'll have a unique ID. And we'll have first name, last name, address, and birthday. So let's talk about address. We probably don't want to have just, again, we want the data in a field, a given field, to be atomic. So we split up name into first and last, and let's say for our application, that's good enough. If that's not, we'd have to rethink this if we needed more complex information, but address. So what do we do about address?
Split it into street, city, and state.
Okay, so one thing we could do is we could have right. So we could do this, and then maybe we could add zip and whatever else, apartment number. So as this gets more complicated, it seems like maybe we're doing two things where we now have a new entity, perhaps. Again, so this will depend on the application. So, this name is maybe an edge case. Maybe we could make that a new entity as well. But I think address could certainly be a new entity. Okay, so we have a customer. So that's one kind of thing we want to deal with. Now we have an address. So for address, we go through the same process. So what are the fields or the attributes or the columns that an address should have? So I think you already wrote that out. So street, in our case, we're keeping it simple, city, state. Okay, so we have an address, we have customers. So why don't we, yeah, so let's represent this. I'm actually going to use this as a diagramming tool. There's a link, I believe. So you don't have to use this tool, but doing some kind of, again, some kind of visual representation of your data is, I think, extremely important. So you don't have to use this particular tool. So there's nothing very exciting happening right now. Move this over. All right. So similar to UML diagrams, we can kind of represent that there's a semi-formalized way of doing this, and there's lots of variations, so don't get too hung up on the details here. But so now that we've figured out, so we'll come back and fill out the rest of the application. But for now, let's just say that all we care about is customers and address. Customers and addresses. I'll just make this singular. So customer and address. So once we have our entities, we need to figure out how they're connected, how they're related to each other. So that's why we use an entity relation diagram. So we have our entities. Now we're going to figure out how they're connected. So let's kind of represent them just on their own here. So customer. And let's do and address. Let me zoom in. Okay, so we have a customer and we have an address. So there's a slight learning curve here for this particular application, but again, you can use pen and paper or whatever you like. So customer, let's add the attribute. So we need an ID. And that's actually going to be a primary key. So PK is just how you express that here. All right. Then we have first. Let's get all these down. Last. Okay. So one reason to use databases is that we can enforce, we can enforce data integrity, and part of that is enforcing certain types and constraints. So for the first, what kind of data should a first name be?
It's string.
Yeah, so it should be a string. So there's a few ways of representing that. I think the most common would be varchar. And varchar, you need to tell it basically the max. So 255 is the max for varchar. There are other types where you can have more text or more string input. So let's just say 100. This is a value that you probably want to determine by, thinking carefully and maybe gathering some initial data. What do we expect? What are potential edge cases? Are we going to get someone who has an extremely long first name? Okay, and then last we can do the same. Let's say it's 100. And birthday. So, I mean, this is a simplification. So there are data types that you can use. We'll just keep it simple and just say it'll be an integer for a year. Okay, and then address. We've got street, city, and state. And again, street we'll do bar car, and we'll say that's, 100 just because. And city, make that 50. And state, we'll have an abbreviation. I think there's just a car. So if we want to use a state abbreviation, we know it only has 2 characters. Something like that. Okay, so now we have our 2 entities drawn out. Well, one question, does address need an ID as well, or only customer?
Wouldn't it be good to have address have a primary key too?
Yeah, I think it would. So by default, every entity that you create should have a primary key. Okay, so I think we're good on the entities now. So how do we express, so let's talk about the relationship between customer and an address. How does that relationship work?
A customer has an address.
Okay. So a customer has an address, has how many? Can a customer have 0 addresses, 1 address, 10 addresses, 100 addresses?
And typically they would have 1 unless we wanted to make it a little more complicated where they could choose.
Yeah, so again, so this is something you would need to kind of determine based on the needs of your application. So if we think about the requirements and we say, okay, we only want customers to have 1 address. So if you think about like your Amazon, your Amazon account or whatever, if you move around a lot, like my Amazon account has like, I don't know how many addresses over the years. So their data model supports that, right? So you can have multiple addresses associated with your account, but you might not want to do that. You might not need to do that. So we could have a customer has 1 address. We could do that. Or even a customer has 0 addresses. Could a customer have 0 addresses?
Even if a customer is homeless, they could have an address that says that they are homeless.
Okay, yeah. So we could do that. You could have some kind of, yeah. So you could have maybe a default case. You could also, maybe your application doesn't really require a customer to have an address. Maybe that's an optional field. So again, you'd have to think about what your application needs to support. But we'll keep it simple here and say that a customer has 1 address. What about the relationship between an address and a customer?
Wouldn't customer need a new field, a new column for maybe like address ID so that that address ID can equal the ID in address?
Yeah. So yes, exactly. Well, we'll get, but before we get to there, I just want to talk in more general terms about the relationship. So we figured out that the customer has, exactly 1 address. But what about the relationship? What about that reverse relationship? between address and customer.
We can keep it simple and just assume that each address can only belong to one customer.
So we could definitely do that. So we could have a one-to-one relationship where a customer only has one address. In that case, it's almost like if we just put this information into customer. Maybe. So customer, we could enforce that addresses have to be unique, but what if, again, we have, a family and the husband and the wife both want to place orders? So again, it just depends on your application. I would say that probably the simplest kind of common thing we could do is to say that it's possible for multiple customers to have the same address. Maybe two people who are roommates living in the same apartment, or a family with kids and parents. So if a customer can only have one address, but an address can be associated with potentially lots of customers, then we'd call that a one-to-many relationship. So this is a one-to-many relationship is the most common kind of relationship you can have in a database. A customer has one address, and address can be associated with many customers, one or more perhaps even 0 or more customers. So yeah, let's go back to what Jen was saying. So how do we actually express that association? How do we express that relationship? A customer can have one address, and address can be associated with many customers.
Is it that little 1 branch, 3 branch notation?
Yeah, exactly. So this is just notation. You don't have to do that, but so what we want to do basically is create a new field in customer. So we'll have an address field, and oftentimes this will just be called like this. So address, whatever the thing is, underscore ID. And what we want to do is associate, we want to connect these two entities through their through a primary key so that it's unique. So we want to have a customer can only have one address ID, and that will be a foreign key, right? Because customer, this is customer, so an address ID is going to be a foreign key because it connects to another entity. And then this is just the notation here for this particular program. We could do something like that, and we'll say it should be connected to address ID. Let's see. I think I might need to do it like this. Okay, that's it. So yeah, again, you can you don't need to memorize the syntax here. And if especially in the beginning, if you don't want to worry about the cardinality, you can just connect it like that. But anyway, so what we have here is a customer. So we can see one in general that now these two things are connected. So that's good. More specifically, this is somewhat standard notation. So a customer can have many, oh, sorry, it should be the opposite. Customer can have right. So a customer can have one address. That's the single line here. And an address can be associated with many customers. That's the crow's foot here. So if we create a bunch of customers and then give them addresses, we should be able to start with a customer and then get the address information. So let's go ahead and try to implement this in a database. So I'm going to take a screenshot. So I have this to work with. I'll split the screen. And so I want to create a SQL file that's going to express what I've done. So we've started with kind of our requirements. We split it up. We created entities. Then we modeled the relationship between the entities. And now we want to actually implement this in SQL. So I'm going to use a script just because I think it'll be easier to do. So I created a SQL file. And in order to create a table, I used the very counterintuitive create table in SQL. So create table, and then I give it a name. So in our case, we'll call it, we'll start with customer. So create table customer. And now we can specify all of the fields or the attributes that we want a customer to have. So first off is ID. And let's say that's serial. So this is just Postgres taking care of that for us. So it'll basically increment by 1 every time you create, so it'll auto increment. So ID serial. And we can also, aside from that, we can let Postgres know, or let Postgres know that we want this to be a primary key. So we have to explicitly say that primary key. And again, the standard, somewhat historical convention for SQL keywords is to use all caps, but I don't want to do that. So we have syntax highlighting so you can see where the keywords are. Okay. So we're going to create an ID, and we're going to let Postgres handle auto incrementing, so making sure that it's unique. And we're also telling it that it's going to be the primary key. So we have our ID. So now we need a first name. And let's say we decide that it's going to be varchar, and it can be up to 100 characters. And last, do the same thing. There are a whole bunch of data types, so you can just take a look at the documentation depending on what your needs are. And
Why?
Yeah.
Why is it highlighting first and last like they're keywords?
Yeah, I'm sure they're keywords. So we could do we could fix that with something like this. I don't think it won't actually matter. I don't think it'll create issues, but probably best to avoid that. So we have first name and last name, and then what do we got? Birthday. We'll call it birth year. And that will be an integer. All right, so I think that's, so yeah, so the last thing we need the last thing we need is a foreign key, which is going to connect us to the address table. So unfortunately, it's slightly more complex to express a foreign key relationship here. But so we're going to have to basically declare this. And then on another line, we can tell it exactly how it works. So on the next line, we'll let it know that it's a foreign key. So so there are a few ways of doing this. You can just create a bunch of tables, and then at the end of after you create all the tables, you can alter them to express the foreign key relationships, which is arguably better because you don't have to worry. So we'll see in a sec that the order will matter here. So foreign key. Address ID. Okay, so now we have created our schema for this table. So we're creating a customer table. We have the primary key. We have all the attributes that we care about. And then we're also adding this foreign key, which connects to addresses. So let's go ahead and write our addresses table. So we'll do the same thing, ID, serial primary key, and we'll have a street. Let's say it'll be a varchar, the max of 100, and a city. I'm just going to say 10 for now. And then state. Oops. States. I believe just car is a thing. Okay. So then I'll remember my semicolon. So let's try and actually get this into our database. So the first thing we need to do is create a database. We can use, because we've got Postgres installed and everything, we do create DB, and we'll give it a name. So this is going to be something like, I'm just going to call it shop. Wait for this to do its thing. There we go. So it looks like that worked. So I can go in and just make sure that I actually created the database. So PSQL shop. And now I'm here. I can describe the database, \D. Okay, no relations. No relations meaning, again, there are like 3 sets of terms for all of this stuff. Relations means table. So I'll quit /Q. And now I want to run this script in my database. So I get a couple ways to do that, but I think the easiest, so PSQL, the name of the database, shop, and we'll pass it the -F flag for file. So we're going to run this file, schema.sql, and you get an error. So I will say that the error messages for SQL tend to be less helpful than for Python or JavaScript. So why might we be getting this error? So it's occurring on line 9, and when you're reading SQL errors, you can think of them as giving you approximate information about what's happening. So it's maybe on or around line 9. And you get an error, relation address does not exist.
It looks like it might be one of two things.
Okay.
Either it's because the address is like a keyword or something because it's highlighted,
Okay.
or it's because foreign key references address was done before the table address was created.
Okay. Good. So let's try testing the first hypothesis. We'll rerun our script. We're getting the same error, so maybe it's not that. So the second hypothesis is that we're referencing something too early. So let's try this now. Now we're getting a different error. Let's go into our database and see what's happening. PSQL shop. So we have address. That table already exists. So let's customer. So we have, looks like we also created this additional table. So we've got some extra stuff here, and let's describe.
Oh, you have made one. Yeah, birthday.
Okay, so we can see we have, if we describe our address table, we have an ID, it's an integer, it's not null. So this is happening when we make it serial and primary key. It's making it not null, so it's not optional. And then this is whatever magic function that Postgres is using to make sure that these are unique. So you have our street and so on. So we're trying to create a database when it already exists. So I'm gonna go back in here. So PS shop and describe all of our tables. I'm gonna go ahead and delete this address test table. So drop table address test. And what just happened?
You deleted that table when you dropped it.
Okay, so let's see if that, I don't know if I can.
You need a semicolon. It went
Yeah.
to the next line.
Yes, so I forgot to add a semicolon, so it thinks, I press enter, so it thinks I'm just doing a multi-line command. So I need to add semicolon, and now it will actually execute. So it gives me some feedback, drop the table. If I run describe again, I can see that the whatever address test is gone. Okay, so I'm gonna jump back out of there, quit, and come up here. So when you're developing, typically you're gonna want to include a statement. So you're gonna want to drop the table if it already exists, because you're gonna be running this multiple times. So drop table if exists, address, and I can actually just add the same thing up here. All right, and let's try running our script again. Okay, so now we have yet another error. So first off, let's go into our database and see what happens. So PSQL shop. So we have these databases exist. So let me, yeah. So let's look at this error again. Cannot drop table addresses because other objects depend on it. So I'm telling it to drop addresses, right? But it's maybe trying to help me out and say, maybe you don't want to do that. And why doesn't it want to do that?
Because the character table is using address, trying to pull out the address ID.
Yeah, because we have this field here, which depends on the existence of address. So if we drop this, then maybe we're gonna create some problems for us. We have null values, or just other issues can arise. So one thing we can add is cascade. So this will basically delete this, and then it'll delete anything that that depends on. So it's kind of just letting me know that this kind of got activated, that this cascade is being used. So it's going to drop both of the tables, which is from the first 2 lines. Then it's going to create 2 tables, which is from the rest of it. So if I go in PSQL test, oh, whoops, yeah, PSQL shop. I'll describe. So again, I have my address and my customer.
So it turned out that the error was because address was being created after customer.
Yeah, so the order, so if we set it up this way, then the order matters, because we can't create this table that references another table that doesn't exist yet.
What if you have 2 tables that reference each other?
Yeah, so you can do that. So another way of doing this is to not include this here. And then at the end, you have an alter. So alter table statement, and then you set up the foreign keys there. So probably that's the preferred way of doing it. So you don't have to worry about the order. You can just create all your tables, and then you have a bunch of alter table statements where you set up all of the foreign keys. Okay, so now we have our tables. Let's try adding some data. We'll call this seed. And what's the basic keyword that we use to insert data into a table? It's a trick question.
Is it an insert statement?
Yes, it is insert. So we'll do insert into, we'll create some customers first. Well, yeah, I guess we should create some addresses first. Yeah, so insert into address. And we need to specify the fields here. So street, city, state, and then values.
State is state abbreviation.
Thank you. So we'll use single quotes here. So 1, 2, 3, main. And And I'll just copy this. We'll do 2 or 3. All right, so we got some addresses. And let's create some customers as well. So insert into customer. That will have first, last, first year, and address ID. Values. Good old Bob. 1990. And then address ID. So this first one is going to get assigned 1, 2, and 3. So let's say he lives in address 1. And she lives at address 2.
I think, didn't you name first name and last name?
Oh, thank you. Is it? Yeah, thank you. All right, so let's try. So we've created our database. We've set up our schema. So now we can insert our data. So PSQL shop, name of the database, the F flag, and we'll give it a file, seed.sql. We run it, and we can see we get some feedback. So it looks like everything worked. We didn't get any errors. So let's go into the database. So PSQL shop. So everything's there, and let's so let's say we want to test and make sure that the information from that we added to the address and customer table is actually there. Just a quick check.
Would you do the describe command /d?
We could, yeah, so the describe will describe the schema basically. So I can look at the address table and I can see that it's got an ID and it's an integer and a street, and I can see all the requirements that I have. I can also see that the address, it is a primary key. Sorry, it's being used as a foreign key. It's referenced by table, the customer table. So I get kind of meta information about the table when I use describe. But if I want to actually see all of the data in the database in this table,
Do the select all statement from the table you want.
yeah, so we can run a query, right? So we've designed our database, right? We've kind of figured out all the data we want to have. We broke it up into entities. We modeled the entities. We've figured out the relationship between or among entities, in this case, just 2. And we implemented that in SQL. We expressed that using this schema. So we kind of set up the framework, set up all the tables. Then we actually inserted specific data into the tables that we created. And now we're going to run queries. So we want to look at that information. So you can do select star, will get everything from address. And we see that looks like that's in there. So we'll check customer as well. So select star from customer. And we get all this information. Bob, Sally. Okay. So I'm gonna quit out of here and we'll create a new file called.
Chad, real quick,
Yeah.
what was the command in the terminal to insert the seed file into your schema or to
Yeah.
connect those two?
So you will use PSQL and then the name of the database, which in our case is shop. HOP. Then we give it we'll pass it a flag. So in this case, -f, which is basically saying, I'm going to give you a file name. And then we will give that flag an argument, which will be the name of the file. In our case, c.sql, but we could call this anything. And then when you run that command, the PSQL command line tool will execute this script in this database.
Okay.
So there are a couple ways of doing the same thing. This is, I think, probably the simplest, but.
Thank you.
Is there a difference in using the -f flag or using the less than symbol, or no, same thing?
No, I mean, it has the same result. It's just that the -f flag is kind of built into SQL, and the redirect operator here is just a bash thing.
Is there a reference we can, a good reference you can recommend that we can go to get these commands?
I think so. There is. Yeah, this PostgreSQL I think this is probably the best single reference, just in general.
Do you mind putting that in the chat?
Sure.
I mean, in the Slack?
Yeah, I'll do that. But in general, just, just searching online, you'll be able to find it. You can also do it. You can also actually do it from inside. I mean, so there's one way. One way is the way I did it with the -f flag. Give this 30 seconds to actually display. There we go. You can also do this, which is just going to redirect. It's going to take this file and basically redirect the output into here. That will work just the same. You can also actually go into the database, and I think it's /i. You can, you should be able to just run the file. Yeah, it takes forever. Yeah. So you should be able to run the file from inside the database with this I. But again, if you want to know like the 10 ways to do the same thing, that's fine. But as long as it works. Okay, so let's write some queries. And again, doing this in the interactive terminal works just as well. But I think it's nice because you get syntax highlighting, and you can just keep the stuff, so you don't have to start from scratch every time. So let's write first off, let's just try to get all of the data. So we'll do select star from address. Select star from customer. And we'll run this file. And that will be, just try it this way. So we get our two queries get executed.
Is there any way to redirect the output to a file?
Sure. We could do this and then when you're actually using this, as part of a web application, Python will convert this, which is basically just string output, into usable Python data. So you don't have to worry about that. But this is basically just like a visual representation. Okay, so we have two tables, and we're getting all this information from both tables. But what if I want to get? I want to see where my customers live. So I could, run these two separate queries and then kind of visually piece it together. So the kind of fundamental way relational databases work is you split stuff up. So you have all of your information, and initially we started with everything in one huge database. So everything is there. It's easy to see all at once, right? So if I wanted to see all of the customers' addresses, if I just had one big table, that'd be very easy. I just select address from table, and I can get all of the addresses. Now, of course, there's a bunch of duplicates, but you can actually just add a distinct keyword to your query, and it will filter all those. So it'd be pretty easy, right? In terms of running queries, having one table is easier. But we had to split it up into lots of tables because there are other problems. Even though maybe it's easier to run queries, it's harder to make sure your data isn't duplicated, and making sure that your data maintains some kind of integrity. So we have to make it more complicated. Yeah, go ahead.
So would you do two select statements and have them have a join command between them?
Yeah, so there's a join command. So that's how, so we have two tables now, but we need to run a query that somehow connects these two. So we have a path from customer to address, right? And from address to customer. Well, no, actually, we have a path from customer to address. So we can use that. So there's a join statement. So join doesn't change the tables themselves in our database, but it will allow us to get back kind of a picture of our database that includes two tables or one more. So the way that works is, so we'll just get everything. So select star from customer. So we're going to grab everything from customer, and we're going to do we're going to join the other table, so address, on So we have a join statement. So we're going to select, in this case, we want all of the columns from customer. And we're going to join the address table. But we have to tell it, we have to tell it how to join it. So there are, again, multiple ways to do this, but the one you're going to use all the time is basically you're going to look for equality. So that's why we have this key. So we're going to join it on customer.id. Sorry, customer.address ID equals address.id. So we're going to grab everything from the customer table, but we're going to join tables. So we're basically going to return one giant table, which is going to be a combination of both of these tables. And how are we going to connect them? Well, we're going to make sure that the customer's address ID is the same as the address. So all of the rows from both of these tables are going to connect, and they're going to connect at this address ID to ID point. So if we run this, comment these out.
Don't you need another select statement for the address table? Oh, you don't.
So you can actually run they're called subqueries, but we're not going to worry about that right now. So here we get one big table which has everything, right? So it has the ID of the customer, and the customer's name, the birth year, and then the address ID. And notice that these are the same. So this is where we're joining these two tables together. The address ID, customer.address ID and address.id. And then we have all of the address table information here. I just want to reiterate that we're not actually altering the data in our database by doing this. This is just presentation. Does anyone have any questions about this so far? So this is, in some sense, this is the trade-off. So we're kind of maximizing certain benefits in our data, where our data is stored, but now our queries have to be a little bit more complicated. And you can do multiple, so there are different kinds of join statements, but there's right join and left join, but you really don't need to worry about that. Just 99% of the time, just join. And you can also do multiple joins. So if we have multiple tables that are connected, you can join one table to another one and then join the third one. So you can, if things are connected in multiple chains, you can access all of it. You just have to do multiple joins. Okay, so let's see, instead of selecting everything, I just want to get the first name and the city.
So instead of select star, you would just do select first name, comma, city.
All right, let's run this query. All right, let me just get that. What if I want to get the IDs? I want to get the IDs for customer and address.
You need to specify from which table those IDs come. So like
Okay.
typically you can do an alias for customer and address, or
So we'll do it. We'll do it wrong first, just so we can see the error.
okay.
So here's the error we get. So no, we're just saying, hey, grab me ID. And before when we used values that were kind of globally unique in the query, at least within the query, we didn't have to do any kind of further specification. But because both of these tables have an ID, it doesn't know what to do. So we get an error, column reference ID is ambiguous. So sorry, Jim, you can go ahead and how do we fix this?
Oh, well, the way that I'm familiar with is just giving an alias to the tables.
Okay.
So
Yeah.
like call customer C and then address A, or you can be, more verbose, but, and then do C.ID and A.ID. And then you could give those aliases as well if you want to specify like,
Oh, sorry, I'm using this.
oh, right, yeah.
This also works. And again, so yeah, if we want to do, so you can actually use the as keyword, or you can just have a space and then, so or you can have as, whoops. So either one will work. But here, so this is starting to look kind of confusing. So just so everyone is clear, we're grabbing that, even though we're kind of referencing it before, it seems like we're referencing it before we're defining it. The SQL engine is doing its own thing behind the scenes, so it's going to evaluate it in whatever order. So it's probably a good time to mention that SQL queries are declarative. So we talked about declarative versus imperative paradigms. So imperative means you are kind of micromanaging, telling it exactly all the steps that it has to do along the way. But with a declarative, you're just kind of saying, it's a little bit more abstract. You're saying, hey, just give me some stuff. So SQL, you don't tell SQL how to go about its business. You just say, hey, I want this, this, and that from this. And under the hood, SQL will take care of actually running the details of the query. So I just wanted to mention that. So if this looks wrong, like you're referencing something before you define it, SQL isn't necessarily executing it in this order. Okay, so here's our customer table. So we're trying to grab stuff from the customer table, and we're saying we want to rename this to C. So anytime we use customer in our query, we're going to need to refer to it by C. So in this case, C.ID. And then C.address ID, and the same thing with address. So we're renaming address to A. So anytime we reference address, we do it with A. And here we're renaming the columns. Again, this is just for a presentation. We're not changing the actual data in the database. So we're just giving it a more descriptive or useful name for us as, human consumers of this. Are there any questions about that? So one way to do this is to rename this. So another way is to let me get rid of this. You can just leave this. You can actually, if we don't, if we don't want to alias this, we can just customer.id address.id. So we're only aliasing one of these column names now, but it'll work the same. So you can either create an alias or you can just use the table name directly. All right, we'll go back to select star so we can see everything. Okay, so let's say I now want to get the state of all of my customers who were born before 1991.
You do the so the same line, copy line 5, but then add where birth year is greater than 1995.
Okay,
On line 8. I think.
so can you just sorry, can you say that again?
Yeah, so after the word customer, that's where I think you should put,
The where?
yeah. And then birth year, where birth year is greater than 1995. 91, yeah.
Let's try that. Okay, so again, we get one of these not so helpful SQL errors. So it's telling us we're getting a syntax error at or near join on line 9.
I think that's happening because the join is part of the from statement.
Yeah, so the where statement doesn't go here. It'll actually go at the end. So here's where we're going to specify. So here's like our general query, and here is where we're adding this more specific condition. So if we run this, you can see that we get Sally. But I only want the state. I only want the state of people who were born, I guess, after 1981.
So then replace the star with state. Or yeah. That worked before.
So is this going to work, or is this going to be, because I'm not specifying the table. Do I have to do address that?
Well, before, when we were getting the first name in the city, we did not need to specify it.
Right. So the answer is that we don't have to, because there's no ambiguity. There's nothing in our custom. There's only one state abbreviation column in both of these. So there's no ambiguity, so you don't need to specify. You can specify it. And some might argue that that's what you should do all the time. But if there's no ambiguity, you don't have to. Okay, and I just realized we've been doing this for an hour and a half. So I think so. This is the basics. It should be enough to get you started on the challenges, which will be a little bit more complicated than this. But if you need help, please, try to figure stuff out, and ask each other, ask me. So this should be enough to get you started. So the basic idea is having multiple tables that can interact with each other, and then making sure that you set that up using foreign keys. And then when you want to run queries on a database with multiple tables, you have to use joins. All right, so that's the basic idea.